So welcome everybody. So again, today we have our STLab Seminar. Today is the seminar is given by Valentina Carriero. She's a PhD student in computer science and engineering at the University of Bologna. And she's going to present some results from her PhD work. She's at the second year of PhD. This presentation addresses a work that has been submitted to a conference under double-blind review. So yeah, just to tell you that this is not to be like circulated until we get the notifications, which is expected by the 23rd of June. So also the recording will be published after that date. And so she's working on extracting patterns from ontologies. And you will see today some of the results that she has got so far. And of course, she will explain the hypothesis and the method she's developed so far. There are certainly lots of points that can raise discussion. So I hope that after her presentation, we will have a live discussion. Of course, as for all seminars, but especially for PhD students, all comments, critics, and suggestions are very welcome for Valentina. So Valentina, you have 30 minutes. I'm going to set the timer just in case. I'll tell you when you have 5 minutes left.
Yeah, I will set my own timer because if...
Okay, very well. So please, the stage is yours.
Okay, thank you, Valentina. So in this seminar, as Valentina said, I will present the initial results of my PhD project. And this is a joint work with, of course, my supervisor, Valentina Presutti, and Luigi Asprino. This first slide was meant to introduce some basic concepts and terminology, but considering today's audience, I think I can skip this. And existing knowledge...
Don't skip it. Don't skip it. There are some.
Okay, so I maybe I will take like 32 minutes because I was 30 without.
You got it.
Okay, in this context, by knowledge graph, we mean a knowledge base that encodes knowledge using a graph-based structure, where the nodes of this graph are real-world entities, and the edges between the nodes are relations between these entities. In knowledge graphs, the knowledge can be formally represented by schemas, for example, ontologies that define concepts that are called classes, and a relation between these concepts that are called properties. So, for example, we can have the node Dostoevsky and Moscow, and the relation was born in. So Dostoevsky was born in Moscow, and Dostoevsky is a person in an ontology, and Moscow can be defined as place. Okay, so existing knowledge graphs use many different and heterogeneous schemas, for example, ontologies that correspond to different modeling choices. And these ontologies can diverge in expressiveness, level of granularity or axiomatization, coverage, names, and naming conventions. And all these is part of the so-called, in a work by Aldo Gangemi and Valentina Presutti, knowledge soup problem, where the semantic web is seen as a knowledge soup because of the heterogeneous semantics of its data sets. And in this context, understanding large ontologies and large knowledge graphs is still an issue. And it is actually a crucial preliminary step for many ontology engineering tasks, such as reusing existing ontologies for modeling data, creating correspondences between concepts and relations from different ontologies, evaluating ontologies, and querying different knowledge graphs at the same time. So ontology summarization aims at making these ontologies more understandable by returning an ontology summary. So, for example, starting from an ontology on cultural heritage that can define concepts such as location, cultural property, technique, subject, we will have a subset or a subgraph containing only the most important concepts based on some measures such as centrality, the centrality of the nodes. But in most cases, for example, when you need to reuse some ontologies for your data, you need to compare different ontologies, and this is not supported. And in order to have an overall comprehension of one ontology, or even one ontology, you need to know all the facts that that ontology can represent, not only the key concepts. These facts can be represented by complex structures that often express a relational meaning, like membership or locating. And we call these complex structures conceptual components. A conceptual component is the intentional counterpart of an ontology design pattern. An ODP defines a set of classes, properties, axioms that are needed in order to answer to certain competency questions. A conceptual component is at a more abstract level, and it is independent of the specific implementation formalization. So, for example, here we have the membership conceptual component, which represents in general the fact of being a member of a collection, and it is implemented in two different ontologies with two different ontology design patterns. The first one is able to answer to a question, for example, such as which are the members of a collection, with the binary relationship as member between a collection and an object. The second one is able to answer also to a question such as which are the members of a collection during a specific time interval, with an n-ary relationship membership with the three arguments, including time. So we can imagine ontologies as compositions of ontology design patterns that implement conceptual components. And starting from a corpus of ontologies, we can have them classified based on the conceptual components they implement with different ontology design patterns. So I think it's already clear how this can impact on ontology understanding and comparison of different ontologies for performing many ontology engineering tasks. Going deeper into our approach, we start from the intuition that an ontology is developed either intentionally or unintentionally as a composition of ontology design patterns, as modeling solutions to modeling problems, regardless their quality. And we formulate two hypotheses. The first one is that the density of the connections between the entities of the same ontology design patterns, so the density of the connections between these entities of the address ontology design pattern and these entities of the ODP event, is higher than the density of the connections between entities from different ontology design patterns. And the second hypothesis is that the combination of the words that are used to describe an ontology design pattern, because ontologies, of course, are not only about topology, but also names, vocabulary, is semantically coherent with the relation that that pattern represents. So, for example, for a pattern about membership, we can have words such as member and collection. This is our pipeline, and in particular, we use community detection for identifying topological phenomena, such as the one in our first hypothesis, and we use text clustering for grouping the detected ontology design patterns based on their terminology. We apply this method on a corpus of ontologies. So the first step is to build a corpus, and I want to introduce you to the two corpora we used in our experiments. We built a corpus of ontologies on cultural heritage. It contains 43 ontologies. 4 of them are ontology networks that are treated like a whole ontology. We exclude ontologies on related domains such as chemistry and also top-level ontologies. For building this corpus, we use the linked open vocabularies repository, and we disseminated an online survey. And we include the inferred versions when possible, that is for 33 ontologies out of 43. Otherwise, we include the asserted versions. The second corpus is actually the dataset that was used in 2020 for the conference track of the Ontology Alignment Evaluation Initiative. It contains 16 ontologies on the conference domain, which is of course less vast than cultural heritage, but still has many subdomains like price or travel. And we were able to generate the inferred versions for all ontologies. So after building our corpus, we need to transform our input ontologies in graph structures that a community detection algorithm can work on. This means that these ontologies need to become graphs that are undirected and unlabeled. We call intentional ontology graph a graph that is derived from an ontology that encodes its intentional level and that is built by following these rules. The first rule generates an edge P between a node D and a node R when the property P in the original ontology has D as domain and R as range. The second rule starts from a property restriction on a class that can be existential, universal, or cardinality, and generates an edge P, that is the property in the restriction, between the class local to the restriction, C1, and the class that is in the class expression, C2. So we still have a directed and labeled graph. So we need a third rule. Here, starting from any edge P in our first version of the intentional graph between a node N1 and a node N2, we generate an undirected and unlabeled edge between N1 and a new node N1 P N2, and another edge between N1 P N2 and the node N2. This new node captures the context of use of the property P. That is, P was used for connecting the node N1 and the node N2. And this is needed because community detection returns not overlapping communities. So if we have just the node P for P, this will end up only in one community, while we know that the same properties and the same classes can be relevant to many different ontology design patterns. So in this way, we enable overlapping communities. As you can see, we do not consider in these rules the hierarchy of classes and properties. So here's an example starting from this ontology fragment. Here, for example, we have a domain axiom on the properties recorded by, and in the ontology we have also the range axiom. So event is recorded by location. In our intentional graph, we have a node for the class event, the intermediate node for the contextualized property, event is recorded by location, and the node for location, all with undirected and unlabeled edges. And the same happens for any kind of property restriction, such as here max cardinality involving a data type property with a data type as range. Some additional notes: when a property has no domain or range, we assume it has our thing as domain range, so we still keep this property in our intentional graph, while we do not consider domain range declarations that involve blank nodes or class expressions in property list restrictions like these. However, we empirically observe that this has no great impact, and at least in our two corpora. There are few cases like this. So now that we have our intentional ontology graphs for our input ontologies, we need to apply community detection to each of them. And community detection aims at gathering together the nodes of a network into groups such that there is a higher density of edges within groups than between them. So it's what we need. We used the state-of-the-art Closer-Newman-Moore algorithm, but after running some experiments, we found that there were many big and with a low density communities that could be split in more meaningful communities. So we found that by running this algorithm recursively on communities with a density lower than the average density of all communities detected at the previous step would improve the results. Community detection returns communities as sets of nodes. So this is an example of a community. After splitting our contextualized property nodes in the original classes and property involved, we apply an additional step that is retrieving the ontology fragment in the original ontology with those nodes that represent the ontology design pattern that we have observed. And we do this, we define a boundary by using some heuristics. So we get the triples asserting the type of the node, domain and range axioms for the properties, inverse super equivalent properties and classes, or restrictions on classes that involve at least one property that is in the community, and also the annotation. So for example, for the node reduction in one of our communities, we get all these triples like also the superclasses or the comment. Now that we have our communities, we are ready to for the clustering step. And since we are working on a corpus of ontologies, if we cluster all the communities from all ontologies according to their vocabularies, we may identify the conceptual components that are shared potentially by all of them. In order to do so, we build a virtual document for each community by concatenating all English labels from the entities of the community. When there is no label, we use the local ID and we split it if needed. And we also remove the repetitions. So starting from a community like this, using the labels or the local IDs, we get a virtual document like this one. Then we disambiguate these virtual documents by using UKB that is based on WordNet. And we also include FrameNet frames that have a close match with the scene sets that in the virtual documents. By using Framester. And we add also more general frames by exploiting the hierarchy of frames. So starting from this first version of virtual document, we get this new version that has all the scene sets, possible frames with a close match, and also possible more general frames. And we use this virtual document for the clustering step. So we used K-means, which is a state-of-the-art unsupervised clustering algorithm for clustering our virtual documents. And each cluster potentially represents a conceptual component by putting together all the ontology design patterns that implement that conceptual component. The clusters that we detect are put in a hierarchical network where two clusters are hierarchically related if there is at least one frame in one cluster that inherits from at least one frame in another cluster. And these relationships between clusters are weighted based on the number of frames that have these inheritance relations. We assign a meaningful name to each conceptual component that is the most frequent frames or scene set, that is the frames or scene set that have the highest frequency within all the virtual documents of the communities of that cluster. And we also add a description that is just the concatenation of all terms that represent the observed ontology design pattern of that component. So for example, here we have two virtual documents that represent two communities, that is two observed ontology design patterns, and they end up in the same cluster that represents the conceptual component event, because the most frequent frame is the event frame that occurs 41 times in the 21 communities of the cluster that come from 13 different ontologies. And from the description here, we can already see that we are talking about different types of events, such as reproduction or cultural. The last step of our method is the generation of a catalog of conceptual components and observed ontology design patterns, where ontologies are classified based on the conceptual components they implement, and where each conceptual component is linked to its ontology design patterns within the ontologies that implement that conceptual component. We also provide an HTML rendering, and all credits for the catalog go to Luigi Asprino. Here, for example, we have again the event conceptual component with the description, and we can access to all the ontology design patterns that implement the event component. And for example, here one from CDOC CRM with also the RDF OWL implementation of the pattern, so the ontology fragment and the whole ontology. So we run this method on both corpora, and as for the intentional graphs, these are the average number of nodes and edges of the intentional graphs. And during the transformation from the original ontology to the intentional graph, we keep about 90% of the original properties and 50% of the classes. So this number may seem very, very low, but actually this is because of ontologies that have a poor axiomatization. And since we do not consider the class hierarchy and the property hierarchy, these ontologies are mostly affected by these rules. So for example, imagine an ontology that has no domain range restrictions, no property restrictions on classes, so classes are not used anywhere. So they are basically taxonomies, and there are many. They do not really implement ODPs in its relational meaning, so it's not a big deal. We found more than 1,000 communities in the cultural heritage corpus and more than 400 in the conference one, with an average of 30 and 26 respectively communities per ontology. By a manual random inspections of these communities, we found that there are patterns that are common to many communities and that actually correlate with the modeling practices that have been adopted for a specific ontology or for a specific ontology fragment. So for example, we will have some communities that are like these two communities. They are bad in the sense that they don't have a conceptual unity. They mix many properties with different heterogeneous meanings. And this is again because of a poor axiomatization. For example, here we have properties that have non-domain and range that are not used in the ontology, or here we have domain and range, but again, that's it. So in these cases, the topology couldn't support the identification of significant communities. Actually, these bad communities could support ontology evaluation tasks, for example, by suggesting in the insertion of new axioms in a specific ontology fragment. And in other cases, community detection just splits too much. So here, for example, we have two inverse properties that are in two different communities with the same classes. So we have duplicates. That's not great, but I want to say that when we retrieve the RDF, our implementation of these ontology design patterns, we include also inverse property axioms. So at least we complete these patterns. And also these two communities end up in the same cluster. Anyway, the majority of the detected communities has a good level of semantic coherence. Here's, for example, 3 communities from CDOC CRM about transfer of custody, destruction, and joining of an actor in a group. And what I want to highlight is that the properties that are clearly inverse property, like joined as what was joined by, or destroyed was destroyed by, none of them have been explicitly asserted as inverse in the original ontology, and still we have them in the same community. We know that ARCO implements many ontology design patterns, and here are some of the patterns that we were able to detect. These 4 patterns are actually specializations of the more general situation pattern that we also could detect in ARCO. As for clustering, we use the elbow method to determine the optimal number of clusters. That is 100 for the cultural heritage corpus and 81 for the conference. With an average of 13 and 5 communities per cluster, respectively. And these communities come from an average of 4.5 and 2.6 ontologies per cluster. The overlap coefficient tells us that our clusters have a good quality because they are very dissimilar. And we also performed an evaluation of our results against the ontology matching task, even if we do not produce ontology alignments. But we start from the hypothesis that given a pair of similar entities to align, because there is a data set, for example, of alignments or a tool, ontology matching tool, they should belong to either the same cluster or to two related clusters. And our results, this experiment shows that our clusters and their relations may be used to improve the performance of ontology matching algorithms. So our clusters identify a wide range of different conceptual components with different levels of abstraction. There are general components that, as expected, emerge from both corpora, like event or membership. But there are also components that are specific to the domain, like performing arts and attribution for cultural heritage, and submitting documents and respond to proposal for conference. Here's an example from the cultural heritage corpus. It's the categorization conceptual component, and we can see here some general patterns from some ontologies. Like concept classifies thing, or classification is classification of thing, or classification in time. And then there are different specialization, like musical instrument classification or photographic heritage classification. Acquisition, here we have 3 communities, and this is from CDOC. This is from ARCO, and actually this class from ARCO is actually aligned to this class from CDOC. And we also have a more simpler pattern, like the binary relationship between an item and an immediate acquisition from BibFrame. For the conference, we have, for example, the submitting document conceptual component. Again, we have the general concept of submission with some content, an author that submits a paper, and for example, deadline abstract submission. Here it is related to an abstract. Here instead, the submission deadline, that is actually a date time, is related to a call. So many different implementations of the same general component submitting documents. So I showed you, I mean, the good conceptual components, but not all clusters are good conceptual components. So for example, there are clusters that clearly need to be split, like this one that has 111 communities from the cultural heritage corpus, where there is no frame or synset that really emerges. So there is this one, the synset agent, that occurs only 14 times in 111 communities, so it's not really representative. And also communities that maybe should be merged, like these two that have the same name. We have also some problems with names, mostly because of disambiguation. Here's, for example, a community that is named Being Employed. But if we look at the communities, we have all this work, occurrences, and it's because FRBR, for FRBR, work is an intellectual or artistic creation, so it's not really talking about being employed. So in general, we need to improve conceptual components extraction. Also, it is interesting to study how to identify and exploit communities features for example, ontology evaluation, like how to recognize bad communities and how to suggest, for example, improvements for refactoring the ontology. We also need to do a user-based evaluation of this method. And it's not that simple because we would need experts in pattern-based ontology engineering. So we are thinking about evaluating this method in an indirect way, like by evaluating a pattern-based visualization tool that Christian Colonna is developing, using that will use in this case our method, or for example using our method for ontology selection or ontology reduced tasks. We will also need to include class expressions in the intentional graphs, and it's something I'm doing right now in these days. And of course, it's important to find an automatic way to link catalogs and foundational ontologies design patterns to our observed ontology design patterns in order to understand how and how much state-of-the-art patterns are used in practice. And of course, an annotation language of conceptual components and ontology design patterns within the ontologies. So there are probably many other things we can do, but I think I'm done for now. So thank you so much.
Okay, wow, perfect timing, Valentina. And
I forgot something probably.
yeah, but anyway, so I hope there will be questions or requests for clarification or comments, so you will have the chance to integrate. Okay, so we have already one hand raised, and by the way, nice talk, Vale. Misael.
Okay, thank you. Very, very interesting talk. I was wondering if you have, or if you have thought about evaluating quantitatively the results. I mean, you might annotate manually an ontology with the implementation of design patterns and see how many of these design patterns are found by your method, and also how many that you found are not correct. Okay, so if you have some precision recall of measurement of your method. Also, I wanted to ask you which community detection algorithm you use, and if you have tried to use another similarity measure for the clustering, like based on embedding, or like BERT, something like that. Maybe too many questions.
Yeah, one question at a time, by the way. Vale, did you?
So thank you so much for the suggestions. And yeah, for the first one, we were just talking about doing what you suggested. So yes, we need, and then, I mean, we did just a manual evaluation. So for example, looking at the results, and I know some patterns from ARCO, but it's just manual. So yes, we were thinking about annotating some ontologies, starting for sure from ARCO, with implemented ontology design patterns in order to see what you said. So precision and recall. So yes, totally. And for the second one, yes, also with the community detection, we use the Closet-Newman-Moore algorithm. There was the reference in the slide, but I can also point you to the algorithm. It's actually very kind of old and state of the art.
Okay.
It is implemented in the Networks Python library. And I also tried the label propagation algorithm, but I mean, it didn't seem to produce better results. And for the clustering, yes, we thought about try to use also embeddings like BERT or something, but we didn't do that. But yes, it's something that we should consider because maybe it produces better results. So.
Okay, thank you.
Okay, yeah, we were talking, Michel, about thinking on how we can exploit these language models to improve, for example, the explanation of the clusters, or but it's still, we thought about it, but, so it's a good suggestion, but yeah, it's something that definitely will be considered. Thanks.
Yeah, the language model works very well compared with previous techniques. So I think
certainly
it's what to try. Yeah.
Aldo?
Yes. Devi...
Okay.
Thanks. How might? Okay, that's it. So thanks, Valentina. Very clear, nice work. Actually, you're you're going to solve the modularization, automated modularization problem in ontologies in the next future. Okay, so my observation is about the role of data about that. I guess you are not yet introduced it within the method, but for example, if you go to slide 34, I like actually to pinpoint specific. Yeah, I did it, but I can't hear. Wait a moment. No, it's not a problem of volume. Probably it's a problem of. So the speaker, same as system. Yeah. Okay. Now I can hear you. Yeah. So you say that should be that one, yeah. By the way, you say that you actually verified that. No, probably it's the next one, 35. Sorry, I missed. Nope. Definitely I was. Okay, forget about it. So you notice that ontologies that okay, this one, 34. It is. I didn't realize it was there. Okay, so the poor axiomatization is something that would preclude the possibility to extract a design pattern from an ontology. However, now imagine this situation. No? You don't have a pure taxonomy because there could be an ontology that has just classes and properties, and you don't have any axiom that links classes and properties. Okay, yet you might have a lot of data that use these ontologies and actually assert property declarations. No? So in that way, you can factor in the ability to infer axioms based on the usage that you have made of this ontology. This actually is a pretty known work. We made something many years ago about extracting ontologies from data based on these loose vocabularies. Still, you can discover patterns there. And this is the case of quite a few ontologies actually that are used, especially in linked data and knowledge graphs that don't axiomatize much. This would be interesting to add in your method as well. No, of course, considering the fact that by using these data-driven approaches, not necessarily you are catching the real intended semantics, intended conceptualization, but on the other hand, it's even more precise, because sometimes you have ontologies that are axiomatized, but they are used only partly or with a special way in a special way in the data. So considering these aspects might be very interesting to reinforce your to improve your method. No, that also becomes even broader. No, you can discover patterns even when people do not know anything about relating decently and axiomatizing vocabulary. Okay.
Yeah, thanks so much. Yeah, we also talked about, including in the approach both the topology, the vocabulary, and the data. So yes, this was something we wanted to do, but I didn't think about the fact that it would improve. It would, improve the results, mostly in these cases. So where there is poor axiomatization. So I think that this is something that it's very interesting. That we will do it. Thank you.
Okay.
I'll stop sharing.
Thanks. Yeah, in fact, we actually considered at the very beginning that we wanted to go, to analyze these 3 dimensions, and then so far Valentina didn't yet work on the data, because also besides discovering other patterns that maybe come from the data and less from even if they are not expressed in the schema, in the ontologies, you can also reinforce the result, the patterns that you discover from the schema. So if the data actually show that, we also thought that data can tell us better how to draw the boundaries, no, for extracting for extracting the implementations, the actual implementations in the ontology. It's just that she's not yet there, but it's something that definitely must be considered. There is a hand raised by Andrea. Of course, invite all the others to raise their hand, and if they have questions or comments. Andrea, please go ahead.
Yeah, my question is somehow related to what you are saying. So what is here the notion of context or boundaries? So how we can detect the clear boundaries in order to identify precisely what the pattern is. So typically, so just also to rehearse what you mentioned about the knowledge soup, another key point for a pattern is the relevance with respect to a specific context, and also its availability, its capability to to identify clear boundaries either around data or in a specific domain. So this is somehow the first question. Then I don't know if it is just for the example or for sake of shortness. In the examples you provided for the results and experiments, I see only 2 tiered structures in terms of patterns. So you have only 2 layers for your patterns. It is always the case, or it is also it is only by chance that you have this kind of structure for your patterns?
Okay, so for the boundary, yeah, that's a problem. By now, as I said, we use just some basic heuristics, so the domain range for properties, and for example, for the property restrictions on classes, we decided to include only those property restrictions where there were properties in the community, not any, of course, property restrictions on one class. But yes, we can improve, the boundary, for example, by using data, and we, of course, didn't still solve this problem. The second question, I didn't really understand. You mean?
The second question is about the structure I see in your examples. If you open the last slides, there are a couple of results, and in those results, I think you are presenting example patterns you were able to gather from your analysis. And this pattern seems to be structured as a, you
mean these slides?
No, the previous one yeah, the previous one, yeah.
Okay.
And okay, yeah, they're more structured. Yes. No, I thought that the structure was based only on two layer connected each other, but this is not the case. You have also more complex structures. Then, yeah, if I can, I have a different kind of questions, which is more about the method. You said that you generate a sort of textual document from the ontology, basically, or representation of the structure of the ontology that then is used for linking your terminology to WordNet, Framestore, so to lexical resources. So you have synsets instead of words.
Yes.
But then you lose the structure. So you have a document without any structure or any relation or any topology or any logical representation of the document. So is there any solution you are thinking about? Oh, first, this is relevant, what I'm saying, or I'm focusing on a wrong problem? And the second point is then, okay, how to cope with this problem?
Yeah, actually, we lose the structure since the beginning because even here, we just concatenate words and regardless if they are from a property or a class, and we also remove repetitions, for example. And so, yeah, we lose the structure and we don't know if reduction agent is together or not. And this is something actually we thought about. So how to preserve the fact that they are like that, I don't know, data entities together and it's not separated. And I mean, I keep track of the provenance of the parts of the virtual documents, but then in the clustering and in the disambiguation, I don't. So I think it may be relevant because actually, if I understood well, yes, if here we have an event narration and not narration separated, for example, I don't know. So no, I don't have any idea how to to consider the structure here for clustering or for using the terminology.
I would like to comment, if I may, on both the comments from Andrea. So one is about the boundary, the first one. So the boundary, so you asked how do you know what the pattern is when it's relevant? Well, as Valentina said and also explained in the presentation, we have some heuristics to retrieve the actual implementation in the ontology for a conceptual component. And these heuristics basically are designed so that so we of course risk to miss some pieces, but we are sure that we don't go too broad, so that we actually draw a boundary which may be too constraining, but we prefer this than also because in this work we are not interested in defining precisely what the pattern is or having a definition on how to define the boundary, but we want to make sure that we can retrieve a good approximation of the implementation of the pattern. So the idea is that if you look at the implementation of a certain component, we point you to a block, let's say an implementation, and then you as an ontology engineer can recognize whether, for example, you want to add another property or another class. So we are not aiming at identifying automatically a formal definition or complete a precise definition of what a pattern is, even because I think that even a human cannot do this. So we are interested in having a good modularization of the ontology, which of course it's approximate, as it's an empirical approach. And as for the structure in the text, so I wanted to remark that on one hand, as Valentina said, because I didn't think about it, but actually we don't need the structure in the text, because we use the text, so we extract so we build the virtual documents because we want to use them as a basis for clustering. So we don't care about the structure while we do the clustering. However, we may experiment on using some knowledge about the relations between these terms to improve the clustering. So this can be a way to use the...
Yeah, no, just to add something about my question about the structure is that, I don't know if it is relevant, the structure of the original ontology per se, but as you are able to gather or to retrieve possible scene sets or frames from FrameNet, and there you have the relations among frames and among other roles and whatever, and frames are patterns somehow, okay, are patterns. So my intuition, my suggestion is there any way to combine somehow the knowledge you have from a lexical knowledge bases that contains frames and other kind of patterns in order to gather patterns from ontologies. So I don't know, I mean, it is just a comment.
Well, we thought, so initially when we looked at the data, the terminology, we thought, okay, how do we identify the frame, the most representative frame? So I don't know if Valentina, you want to answer this, or you want me to continue, but if you have something to add, I will go after you.
No, you can go.
Okay. Sorry, no, really, I mean, of course, but so we thought, so we had this basically bag of words, and initially we didn't even remove the repetitions. So we removed the repetitions later because we noticed that the results were noisy, and we tried, and actually they improved. So we had this bag of words, and we thought, okay, now that we have this, so we had actually initially the same intuition that you have. Can we like match frames and their roles? So can we identify that here there is a frame? So can we match what is here with the possible, like if we are recognizing frame occurrences, basically. And this is certainly an hypothesis that you may be able to do it at least manually, like you look at it and you can try. But then we said, okay, no, I mean, how can you do this? Because it's not a text with a sense, no, that you can try and do frame recognition and frame detection. And at least to our knowledge, so we didn't identify any way to do this easily or without focusing on that specific problem instead of what we had to achieve. And so clustering actually was clearly a good way to go, at least to put these things together. And then the disambiguation and the frame, the relation between scene set and frames that Framester gives us were at least so far enough to have a good result in terms of approximating again what's the most representative frame. So we use basically mainly frequency, and by removing the duplicates, this was even more representative. Of course, this can be improved, but more than trying to recognize the frames, because the frames are very generally defined. So it's really, so how can you detect these are anyway? There's not a sentence where you can run, I don't know, Fred or a frame detection tool. So I think that instead trying with the language model to see if we can improve the way to summarize or adding meaning to describe the cluster is probably a better way to go. But
yeah.
So this is
okay. Yeah, I don't know if there is also a future work that aims at including also ontology design patterns as a a repository of patterns for aligning for alignment, or as a background knowledge for the recognition of existing or of patterns, because it could be also another strategy or a possible direction that can be followed.
Yeah, we thought about including in our corpus, in our corpora, for example, foundational ontologies such as Dolce, and in order to see where how Dolce is split by community detection and where Dolce's patterns end up in which clusters, in order to see what we can kind of align. So yes, also this is something I will do probably tomorrow. So something interesting, I think.
Yeah, actually, this thing is, I think it's really, I don't know what Valentina will be able to get from this, but putting Dolce or other, we want to put Dolce because we know that there are many of the general patterns that are used, or so if we end up actually having the Dolce patterns distributed coherently with their with their specializations, I think this would be a powerful result, because I think many of us know that understanding what's the general pattern that you can reuse when you have a local or a specific, a domain-specific vocabulary, automatically, of course, I mean, this is the problem of matching your competency questions, your vocabulary with the general pattern that you can specialize. So if Valentina's method, with probably some adjustment and improvement, is able to do this at least at a certain extent with good results, then I think this would be a very powerful result. Also for reusing the method in another context, such as identifying, having the competency questions and now tell me what's the pattern I need to reuse.
Mm-hmm. There's no question. I have another comment, which is nice to discuss here. I don't think it is very related to what Valentina did so far, but I think it closes somehow the loop. Once we have the patterns and the modules, and we want to create a new ontology by using patterns, a common issue I have is that when I import an ontology with protégé, for instance, or a single pattern, I am provided with the whole pattern or ontology. And this is a bit annoying, because in many cases, I am really interested in few concepts or in a small part, which is the real pattern I want to use. But there is no working, to the best of my knowledge, there is no working extension of OWL or protégé that allows us to use pattern or any possible solution like OPLA that allows to annotate ontology modules. And I just did the work on patterns, and I had to reuse parts of ontology networks in another view of the same ontology network. And I was forced to redefine concepts and relations instead of importing the whole ontology or whole modules. And this is, something that goes in the direction of identifying patterns, reusing patterns, and reusing pattern in a feasible way. That means I want to use patterns, not whole ontologies or whole modules. And sorry for the big.
Need to redefine OWL at first, and then because the semantics of import is to import all the axioms from the imported ontology. So you first need to redefine the semantics of a new import, and then also you need a vocabulary for.
No, it's fine.
Yeah.
I understand that the semantics of import is to import the whole ontology or the whole artifact you are pointing out. The problem is probably about how it's visualized. So if I import the whole ontology, this is a logical fact. But as a designer or user, I want to be displayed only with the part I am interested in. And I think that the two things should be tackled in two different ways. So the visualization part and the design part of the ontology from the logical meaning of the axioms like the imports. And that's true. Just for using the import, then you are right. If you want to do something that allows to import only logically the part you want to use, then we have to redefine OWL or to define a new axiom. But I think that the problem can be tackled from different perspectives. But I don't want to spend other words on this topic, because I think that we are going out from the original scope.
I think Valentina wanted to comment. Vale, you wanted to comment?
No, I just wanted to say, so that would be, I mean, the import of a module, so of a specific pattern you want to reuse. So yes, I mean, I think it would be very useful, and so maybe a tool that is specific for this use, I don't know, so that splits an ontology, and then you can, but yes, I don't know if you need some specific, I mean, not OWL imports, of course.
I don't think it's a problem of the language. Well, of course, you can have a primitive in the language that allows you to do it, but I think this is more a problem of implementing a way to do this. So this is a problem it's not a new problem, clearly, because when you study modularization or ontologies and patterns, so this is the first thing you end up having as an issue. So when we developed the catalog of patterns in Neon, so that was the first the period, you know, when we started working on the concrete implementations of patterns. And so we're talking about 2006, maybe it was, like something like that. Anyway, so in that project especially, there was also a lot of work about modularization, taken mainly from a logical perspective, no? Like Andrea was saying. And in fact, Valentina's work, I think that what you, Andrea, say, indeed it's related to Valentina's work, it's not out of scope. So what Valentina's method instead takes a designer perspective. So we want to know what the ontology talks about, and we want to identify those parts of the ontologies where this is asserted. So we are not caring about if I reuse that part, what happens in terms of consistency if I take it out from the whole ontology, because usually this was the perspective applied to ontology modularization, like making sure that you can control consistency, the whole consistency while you were modularizing or extracting a module. I remember that we also did some work. Actually, we did an implementation that now it's not available. So there was a tool, but it was developed for the Neon toolkit. So it's now like other things. So we actually did develop some of these supporting tools that then went into, you know, we didn't have the resources to re-implement the same tools for Protégé, for example. So we did them as plugins for this toolkit that then was dismissed, and so they got lost. But there was a tool that we did, which was actually an XD plugin for the Neon toolkit, where you could copy basically a pattern from the ontology and reuse it, you know, reuse only the part that you wanted to reuse. So you would clone it. So I remember that we defined two operations. So one was cloning, which would mean I copy, so I use this pattern from this ontology as a template and I create a new one. So we had this supporting tool that would basically copy the structure. And the other one was, there was another one, like the extraction, I think, that I don't remember anyway, because now it's long ago, but we had this idea that you would want to reuse only part of the ontology. And you wanted to have some tool that would implement this, like while you are editing your ontology, instead of importing the whole thing, you just copy the part that you want. So in principle, you could have also a primitive in OWL, and let's imagine an extension with the like partial import. The problem is that if you do this, then you have to face all the logical consequences and properties. So I think this is more adequate for a pragmatic approach. And I think that, so one of the possible evolutions of that Valentina is thinking for her work is also to annotate automatically the patterns that she discovers, because we can go always from the conceptual components to the actual classes and properties and axioms that are involved, so that you can basically, for example, if you have a tool that understands these annotations, you can say, okay, now copy or clone this pattern in my ontology. So I think that actually Valentina's work can also have an application in this kind of very pragmatic ontology engineering task. And okay, so is there any other comment or questions or curiosity, or even other suggestions? So we had very nice suggestions. Some of them we already thought about them, but it's very good to hear that, you know, it means it makes sense if also others have the same ideas. Is there any other question or comment? Okay, so I think we can thank Valentina again for the very nice talk. Good luck to all of us for the notifications. But anyway, this is a cool work, so we will publish it anyway, regardless. ISWC, and I'm saying this in the recording, so after the notification, they can hear that we don't really care, because we know it's really good. I honestly think it's really okay. I'm biased, but this is something it's there since very long. And this is the first time I see a result that can have an impact on a pragmatic modularization of ontologies. So thank you very much, everyone. Martina will circulate the details of the next seminar. Who will talk next week, Martina?
Margherita. Okay,
so Margherita will be the next. So I hope to see you all there. I expect to see you all there. And have a good day. Thank you very much.